Thank you. Good afternoon, and thank you for coming to my talk. I'll describe a small and very simple step towards learning small lexicons for CCG semantic parsing. This is joint work with Yoav Artzi and Slav Petrov. Yoav did all of this work when he was an intern at Google, and he could not be here. That's why I'm giving the talk on his behalf. So in semantic parsing, the goal is to take a natural language sentence and produce some kind of a logical representation. So one key aspect here is that it's a very heavily lexicalized process. So over here in the example, the words the red, and hallway, they have a formal representation of meaning, which is highlighted in red over there. And then it composes with the surrounding words, which also in turn have their own representations. And this compositional process happens to create the final logical expression for the whole sentence. So a key component, therefore, because it's a lexicalized process, is a lexicon. So most semantic parsers have a lexicon like this, where the words and phrases are associated with logical expressions, which are the formal representations of their meaning. So today, the focus is to learn a compact lexicon, a small and compact lexicon without many spurious entries in it, but keeping the performance of the end goal or some task better or at par with other baselines which are popular in the area. So we focus on one particular formalism here, which is combinatory categorial grammar. It's a popular framework for semantic parsing. So in a CCG, what happens is that there is a sentence, there are words and phrases which have their categories, which have both syntax and semantic components in it. And then there is a combination process. Over here, it happens from top downwards to create the eventual logical form. Now, a CCG contains a lexicon and a bunch of combinators, and the focus here is on the lexicon. So formally, we express the sentence as X, the parse tree or the derivation Y, and Z represents the logical form. Now, at the onset, I would like to mention that we use this notion of a factored CCG lexicon, where the category for a string is broken up into two parts, a lexeme and a template. In the lexeme, there is a natural language string, walk over here, and the domain constants, which are move and direction for this example. And then there is a template where there are slots which associate with the strings and the domain constants. And this prior work has shown that this helps in generalizing to new data at inference time. So we'll revisit the lexeme and the templates later on. Now we use a log linear CCG. In a log linear CCG, there is a lexicon lambda, there are model parameters theta, and we define the probability of a parse Y and the associated logical form Z as a log linear model. Here, X is again the sentence, and phi is the feature function. So this is a typical log linear formulation. Now, what happens right now in the community, usually, the parse tree or the logical forms are not really directly provided to us. We have some kind of indirect signal from which we learn a semantic parser. So supervision is in the form of a weak signal. So here is an example. This is one particular task, which is the task of navigational instructions and following those. So over here, walk to the sofa is an instruction, and we have a signal in the form of move forward and then move forward. Okay, so this is an agent that is moving in some closed world. Now what happens is that given this kind of a signal, we have to learn a model. So what happens is that once this signal is provided, we generate possible logical forms given the current status of the combinatory categorical grammar model. And if we call this Z sub all, only a fraction of these result in the current execution. So we define that to be Z sub plus. And the way we optimize likelihood is to push all the probability mass towards these positive logical forms that result in the right executions for this particular task. And you can imagine a similar situation for other tasks. Now, another thing of note, this is also nothing new, the lexicon lambda is also not provided to us, so people often learn the lexicon while training the model. And one thing of note over here is that we can imagine a massive lexicon that associates every word or phrase in our training data with every possible logical expression. But that whole space is huge and intractable. So what one does usually is build up this lexicon iteratively while training, which also redefines the model parameters, and then this happens for several iterations. So that's the convention of learning these CCG models. So to reiterate, basically the lexicon is learned, the model parameters are learned, but the combinators, which are few in number, are predefined. So we learn the lexicon and the parameters at the same time. Now, the focus of this talk is to learn a small lexicon, because often we have seen from previous work, I'll show you some examples, the learned lexicons are very large and noisy and often are not interpretable. And we make global learning decisions by looking at the whole corpus at one iteration of the training. So the way I will present this is by taking existing online algorithms, then modifying that to be a batch learning process where we look at the whole corpus and then make parameter updates. And finally, we will introduce two things. One is something called voting, and the other is pruning the lexicon. These are two strategies of controlling the size of the lexicon. So here is what online learning looks like. Basically, there are t iterations over the data, and for each data point, 1 to n, we generate new entries for that data point and add that to the lexicon. And then we compute some kind of an update, often some derivative, and we apply the update on our model parameters. Now, so one thing to note over here is that the step gen entries, which is this abstract step of generating new entries for the lexicon, they're generated on the basis from only one single data point, and these are greedy decisions which are not revisited in later stages of learning. So the goal of this work is to fix this by controlling the lexicon by looking at the whole data at one point of one iteration of learning. So this is an actual lexicon for the word chair. Note that there are domain constants on the right-hand side, like hall, corner. These things are being mapped to the string chair. So this is an actual lexicon for this task that was learned by an online learner. So this is very noisy, and there are a bunch of other noisy entries in the lexicon which I'm not showing. So what we do here is that we take this step gen entries, and we see that, again, this is basically an entry over here is broken up. The category has two parts, a lexeme and a template. So this is very important. The templates are usually fixed. So the templates are usually fixed from the beginning. All we need to learn is to combine the templates with lexemes, which map strings to constants in the domain. So just to reiterate this, in practice, we learn new lexemes, which are mappings from natural language words and phrases to the domain constants, but we learn how to associate them with the templates, which are just generic categories having slots in them. So we will see later how global corpus-wide statistics are used to control the lexeme learning process. So let's look at a batch version of the learning algorithm. So the batch learning, I will first show vanilla batch learning, which is a transformation of online learning to batch learning. And then I will introduce voting and pruning, the two new things that we propose in this paper. So this is what batch learning looks like. It's very, very similar to online learning. The difference being that we make two passes through the data. So in the first pass, I hope you can see the highlighting here, we generate entries for every single data point and then collect all of them together at the end of the pass. And once that is done, we make another pass through the data to compute derivatives based on this large lexicon that we constructed by looking at the whole data set. And then we do a regularized batch update at the end of the second pass through the data. So this is just vanilla batch learning. Okay. So note that what we are doing here is we collect these small lexicons which are generated for every single data point, and we take a union of those to create this larger lexicon after making a pass through the data. So this is again a monotonically increasing step. So what we introduce here is something called voting. It's a simple thing. Instead of adding all these entries that we generated, we vote the entries by looking at the whole data set. And this voting process controls the new entries that are being added to the lexicon. So let's look at the details of this vote process. So in summary, what voting does is it looks at every data point and collects votes for the lexemes for every single natural language word or phrase. And then we select the lexemes using some strategy. We have two called max voting and consensus voting. So a concrete example will show what we do. So each data point has a budget of 1 per string, and votes are summed across all data points. So for example, let's look at only 2 data points. And there are 2 strings, chair and face. For the first example, chair is mapped to 2 domain constants in the 2 lexemes, and face is mapped to 1. And in the other data point, it's 1 less mapping from chair. So the way voting is done, the aggregation of votes is basically for chair. For the first data point, the vote is divided into 2 parts, half and half, while face gets 1 lexeme for face gets the whole vote, and the similar thing happens for the second data point. And when you aggregate all the votes across all the data points in the corpus, it results in this. Now here, once this aggregation is done, we can have some strategy of choosing only 1 lexeme per string. Okay, that's what we do in this voting strategy. And that is done in the first strategy that we have, which we call max vote. It takes the lexeme that has the highest vote. So over here, we see that the word chair is mapping to the domain constant chair in the world, and that is chosen as the new entry to be added to the lexicon. And we discard the other one. So this is max vote. Now, let's consider this example where chair now has been mapped to more domain constants. And what happens here is that you will notice that it is being mapped to multiple things like hat rack, easel, and so on. Okay. Now, although there are multiple data points which associate the word chair with the constant chair, there are other things that like it's being missed by certain data points, like D4, where chair is only mapped to easel. So what happens in such a scenario is that we again accumulate all the votes, while the total votes, when we aggregate them, we notice that easel is getting the maximum amount of votes when you aggregate them across the corpus. So what is really happening here is that more data points, although they support the correct lexeme, which is chair, their votes are wasted on weak candidates. So basically the votes are divided into multiple examples, multiple constants, for example, in the first data point, but so therefore they're wasting their voting contribution on weaker candidates, which appear in other data points. So we have this second strategy, which we called consensus voting, where what we do is we allow data points to redistribute votes from weak candidates. And the way this is done is like this. So we aggregate votes, we discard the weakest candidate lexemes after aggregation for the whole corpus, and then for each string, we select the lexeme with most votes. So let's, again, let me walk you through an example. Basically, for this case, when we aggregate all the votes, at the end of the process, we see that the lexeme with turn and direction as the domain constants has the least number of votes, and we discard it. And once we discard it, those lexemes are also taken out from the data points. And then we do the aggregation process again. And now we see that in the next iteration, the weakest candidate is hat rank. And then we discard it again, and we remove it from the data points, and then we reiterate. And at the very end, when all the votes are, when this process converges, we notice that the weak candidates on which we were wasting votes are eliminated from our collection of data points. So sometimes there are exceptions when there are data points for which we cannot do any parsing. We don't discard entries when there is only one option. Now, this consensus voting process, at the end, again, when it converges, we select the best lexeme in terms of votes. So this is our voting process that happens after we create these data point specific lexicons. The formal description of this is in our paper, so I encourage you to look at it. Now, we also do another step of controlling the size of the lexicon, is something we call pruning. So what happens is that after we compute all the updates, we remove entries from the lexicon that do not participate in a max scoring parse. So a max scoring parse is one that results, that has the high score and also results in the right executions. So we remove those entries from the lexicon, which further controls its size. And finally, we do the updates. Okay, so this is the basic outline of our new method, which is very simple, and we will see how it controls the size of the lexicon, removing spurious entries. Now, one thing to note here is that a lot of related work uses this kind of lexicon learning, and this work is going to be relevant for that kind of, like this whole array of applications. But here, we only focus on the executing instructions task, which was recently visited by Artzi and Zettelmeier. So what happens here is that we execute instructions, like in a closed world. There are instructions, and the agent has to follow those and execute instructions. Now, the form of supervision comes as executions or steps that the agent takes in the world. And during learning, we validate executions of different interpretations against the demonstration. In our experimental setup, we implemented it in the University of Washington Semantic Parsing Framework. We use beam search for executing sequences of instructions. So what happens here is that for one sample, we generate several candidates and in a beam, and that happens for many consecutive instructions. At the end, there is a sequence of instructions that the agent executes, and we evaluate that against the gold standard. There is a seed lexicon which is used to create the first lexicon, which is updated iteratively. There are various features whose detail I won't go into. And finally, we only consider executable parses, only executable parses as complete. Now, here are the results. There are a bunch of models or methods over here. So the numbers I'm showing here is the F1 on sequence executions. So AZ13 is Artzi and Zettelmeier 13, a paper from last year. We add pruning and performance improves a little bit. The batch baseline is better than both. And then we use max voting, which further improves performance, followed by consensus vote, which goes down a little bit. But then once we add pruning to the batch baseline, and then along with voting, the performance goes up again. So the final numbers are really quite, it's much more than the baseline of Artzi and Zettelmeier 13. Now, at the same time, when we look at the lexicon size, there is a drastic decrease in the size of the lexicon when you compare the baseline and our final model, which does consensus voting and pruning. One thing of note, however, is that single instruction execution performance is more or less same across all the models, which is an interesting result. Now, here is the overall summary. comparing AZ13 and our approach. This is the summary from the previous slide on this Oracle corpus. So again, sequence performance is quite good, while the lexicon is much smaller. Finally, we have numbers on the SAIL corpus, which is a much more noisier corpus, but also for executing instructions. Here also the trends are the same. We compare with Kim and Mooney, another baseline, which is worse than either AZ13 or our approach. And also the lexicon size is much smaller in our case. I won't have time to go into these qualitative results. These are there in the paper. Basically, we have much smaller number of lexical entries than the baseline. Sometimes what happens is that some words which are not semantically salient at all for the domain, we just remove those words from the lexicon altogether, which is great. So finally, to conclude, we introduced 2 voting methods to globally consider lexical entries during learning. We integrate lexicon pruning into the learner, which was not there in prior work. And we show the benefit of more compact lexicons in system performance. Thank you.
Thanks very much. We have a few minutes for questions.
Why do you think that single sentence performance didn't go up, but the full instruction did? It seems like those should be highly correlated.
We have tried to analyze that a little bit. So what happens is that often spurious entries lead to the right execution. But when the lexicon size is smaller, the beam search process doesn't suffer from the mistakes from the individual instructions. So often the good parsers are ranked higher in the beam than the single sentence case. That's our hypothesis, but I don't have a very good answer for this.
You happen to run this without the redistribution of votes for weaker candidates to see whether it was ganging up effect?
So that's the max vote approach, I think. So, right, so where we do not redistribute the votes, that's shown in the blue column at the very end. It's a bit worse than only pruning, but the lexicon size is much smaller.
I guess what I was asking is within that, do you see weak candidates gathering enough votes over time?
Right, yes, so that's, we haven't examined the lexicon with only max vote at that. We should have done it,
Thanks very much again.
Thank you.